Hello everyone, and welcome to the 10.4 video where we're going to be talking about the properties of logarithms, and we're going to be practicing the properties of logarithms as well. And one of the first properties that I find handy is something called the change of base formula. And so let's take a look at this first example and explain how it relates to this in just a second. Let's say that you wanted to plug this into your calculator to figure out what decimal approximation you have. The issue is, in your calculator, you're only going to see two buttons when it has to do with logs. You're either going to see a button that just says log, which is assuming log base 10, or you're going to see a button that has the ln, which is assuming log base e. So there is no log base 20 you can plug in. In this one, there's no log base 4 you can plug in. And so what the change of base formula says you can do is if you have log base a of x, you could take log base 10 of your argument x and divide that by log base 10 of your base of a. Or you could do ln of your argument of x divided by ln of a, and it'll get you your decimal approximation. So in this first example, what you could do is either log base 10 of 175 over log base 10 of 20, or you could do ln of 175 over ln of 20. Both of these would get you the same decimal approximation. And it really doesn't matter which one of these you use because they're both really just using this as a ratio situation. If you plug this into your calculator, you would get 1.724. If you plug this one into your calculator, you also get 1.724. So the answer is this either way. The second example, if you want to do the change of base formula, find a decimal approximation, you would do either log of 0.045 over log of 4, or you could do ln of 0.045 divided by ln of 4. When I plug both of these into my calculator, both of them got me the answer of negative 2.237. So change of base formula is helpful sometimes, so I wanted to start with that rule. So now I'd like to go to the more popular properties of logarithms, where we have a product property, quotient, so really a multiplication property, a division property, and something called a power property. So in order to understand, let's start with the product property. In order to understand logarithms, remember that I've been saying a lot that logs are exponents. So let's relate something that we know to this new property. What if I said x to the second times x to the fifth? You might remember from the first video in this unit that if you have two bases and you're multiplying them, you end up taking the exponents and adding them and getting x to the seventh power. So what we end up doing is going from a product or to multiplication, and then we end up using a sum. In a similar way, because logs are exponents, we take a look on this side of the equation or this property. We have a log of a product which is similar to the exponent on this side, and what it ends up being is the sum of exponents, or sum of logs. The reason that these are the same is because logs are exponents. So if you have log of a product, two things multiplied, what you're really doing is adding the two exponents together, because logs, again, are exponents. So that's where this rule comes from. A common mistake, and I'm going to do these in blue over here, a common mistake is for students to think that this is true as well. Log base a of x plus y, some students seem to think that that's the same as log of a of x times log of a of y. This is not true. You can't go the other way. You have a single log with a product, and that gives you two separate logs added. It doesn't work the other way around. It isn't log of an addition equals a multiplication. It has to relate to the exponent rules that we already know. The quotient property ends up being a similar idea. If I gave you x to the fifth divided by x to the second from the first video in this lesson, what we ended up doing was subtracting the two exponents and getting x to the third power. So to relate that, what we really have is a quotient or division, and the quotient eventually leads to a difference or subtraction here. So this log rule is saying log of a quotient is equal to the difference of logs, which is another way of saying the difference of exponents, which makes sense because here we did a difference of exponents, here we did the sum of exponents, which is where the other side of this equation is coming from. And again, a common mistake that happens here is it's tempting to think that log base A of x minus y equals log base A of x divided by log base A of y. But this also is not true because log of a quotient, the single log of a quotient, leads to the subtraction of logs. It does not work the other way around. This last rule, the power property, I want you to remember this rule from exponents. X squared to the fourth. When we had x squared to the fourth, we ended up multiplying the exponents and getting x to the 8th power. And so what you're really doing is you're saying you're raising an exponent to an exponent. So this log, remember, log base A of x, that is an exponent. So you're taking an exponent and you're raising it to an exponent. So here, when we did an exponent to an exponent, we multiplied. So the reason that this side is n times log base A of x, what it looks like is that the n is coming down in front, which is true. But what you're doing is raising an exponent to an exponent, which is multiplication. So you're taking the first exponent n and you're multiplying it by the second exponent log base A of x, which is why this rule works. Now I know that not everybody wanted to know why these things work, but I feel the way that I teach, I don't like to explain, oh, here's a property just because I said so. I wanted to show you how this related to exponent rule. So I hope that some of you appreciated that fact. So please make sure that you have written these down because it's good to know why things happen. For the sake of not getting too overwhelmed though, at this point, I want to erase this work that I did here because I want to use these rules and not get too bogged down. You can definitely rewind this video if you missed anything, but I'm just going to leave the rules here so it's a little bit more clear where I'm getting them from. So now I want to apply these rules. So this first direction says we want to expand the expressions. So when we're expanding, what we're going to do is go from the left side to the right side. So I'm going to write a little note here that we're going to go from the left to the right because you're going from something more condensed to something more something longer or expanded. And so if we look at this first one, this says ln of 8 times x squared times x cubed. And this rule reminds me of this first product property. Log of two things multiplied leads to two separate logs being added. So in this example, we have 1, 2, 3 things being multiplied. So what we're going to do is create 3 separate logs or 3 separate ln's. So this is going to be equal to ln of 8 plus ln of x squared plus ln of y cubed. Now, that's not the only rule we're going to use though, because if we're trying to expand, we're trying to make this function as long as possible. So the second thing I'd like to point out to you is this power property. That again, when you have log base A of x to the n, it turns out because you're multiplying the exponents that the n comes down in front and you're multiplying. So this doesn't have an exponent. This one does. So the 2 is going to come down in front. The 3 is going to come down in front. So our final answer of expanding would be ln of 8 plus 2 ln of x plus 3 ln of y. The second example, log of division or log of a quotient. If we take a look back up at this rule, the quotient property, log base A of two things being divided ends up being 2 separate logs being subtracted because of the exponent rule. So this is the same as log of root x minus log of y. Now, the second thing to always think about when you're expanding, again, is this power property. It doesn't look like I have any exponents, but what I want to remind you is when you see something when you're taking the square root of something, that really means you're raising it to the 1/2 power. So you actually do have an exponent in this problem, which means if I make this page go down just a little bit, that means that my final answer would be this. Bring the exponent down. If I expand it, it would be 1/2 log of x minus log of y. So these next two examples are definitely looking a little bit more complicated, but I'd rather show you these in the video so you're aware of them. So the directions are still expand. So we're still going to go from left to right with these expressions, go from the less complicated to the longer, more complicated. So this time we have ln of two things being multiplied on the top. The x squared is multiplying the square root. Then we're dividing by x minus 2 to the fourth. So I'm thinking that we're going to be using both the product property and the quotient property, and probably even the power property, because we are multiplying in the log, we are dividing in the log, and we have some powers in the log. So first, the top. If we are multiplying, that leads to two exponents or two logs being added. So this would be ln of x squared plus ln of root 5x minus 4, but then we're dividing by x squared, x minus 2 to the fourth. So that means that we're really subtracting ln of x minus 2 to the fourth. So now we've at least expanded it, but now we need to use the power property, and we need to remove the exponents. Before I move some exponents down though, remember that square root means to the 1/2 power. So this is still ln to x squared plus ln 5x minus 4 raised to the 1/2 power minus ln of x minus 2 to the fourth. Now I'm going to move all my exponents down in front to continue expanding. So it's 2 ln of x plus 1/2 ln of 5x minus 4 minus 4 ln of x minus 2. And this is my answer because if you take a look at the properties, there is no property of ln of a subtraction. It's only log of a product and log of a quotient. There is no rule that has ln of a subtraction either way. So this would be my very long answer. Number 3 looks similar in idea, but the reason it's a smidge different are really two things. One, the entire thing has a square root on it, and two, there's two things in the bottom and not just one. So let's break down both of those. My suggestion would be thinking first that this is the same as log base 3 of a to the 7th over b c to the 5th, and all of this is really being raised to the 1/2 power. So what I would do before breaking up this into addition and subtraction is I would put the exponent down in front. So what we would have now, or what it would look like, is 1/2 in front, log base 3 of a to the 7th over b c to the 5th. And so this 1/2 now applies to everything that we do with the rest of this log. So I'm going to put the 1/2 in front with a big old bracket, because now everything else, the 1/2 is multiplying it in front. And so a to the 7th is on the top. So we'd have log base 3 of a to the 7th. And now, if both of these are on the bottom, what you're really doing is you are subtracting log base 3 of b c to the 5th. But now within here, you have b times c to the 5th, which is this first property. So you can really break this piece up into two logs being added. So here's what we have. 1/2 bracket log base 3 of a to the 7th minus all of log base 3 of b plus log base 3 of c to the 5th. The reason I put parentheses here is that technically you're subtracting all of this, but now some of you might be thinking, if I subtract, that negative is really distributing to both of these. So you have 1/2 log base 3 of a to the 7th minus log base 3 of b, then minus, because negative times positive is negative, log base 3 of c to the 5th. So to help some of you, something that I'm going to be doing as this process is going further, if you have two things in the denominator, what ends up happening is both of these things end up being subtracted down here because they're in the denominator. If you have two things in the numerator, like this first example, they are multiplying, so you add them. If you have two things in the denominator, they're both dividing, so you're going to subtract both of them just to help do a time save. You don't always have to do this green step. It's just there to help you understand why step 1. So now what I'm going to do is I'm going to move the exponents down. This is going to come down here, and this is going to come down here. So we're going to have 1/2 bracket 7 log base 3 of A minus log base 3 of B minus 5 log base 3 of C. And then the 1/2 is going to affect every single one of these. So you're multiplying all of the lead coefficients, or dividing it, multiplying it by 1/2 or dividing it by 2. So our final answer would be this: 7/2 log base 3 of A minus 1/2 log base 3 of B minus 5/2 log base 3 of C. Now this problem was quite a doozy, I would say, but again, I would rather show you how to do it than expect you to do it on your own at first. So please remember from this process that if you see anything that's being divided, both of those things eventually are going to subtract down here. Okay, now let's go the other direction. If I'm asking you to condense the expressions, this time you're going to go from right to left. You're going to go from this side to here, or from this side to here. And notice, if you're going from the right to the left, you're going from 2 or more separate logs to 1 single log. So if we want to condense, we want to do the power property backwards as well. We want to go from here back to here. So we want the exponents to be back on top because the whole function is more condensed. So if we take a look at this first example, that 2 is going to go back up as an exponent. So we'd have log base x squared plus ln of x plus 1. Now if I have 2 separate ln's being added, that is the same as the ln or log of the arguments being multiplied. So I'm going to make this into 1 single log, and I'm going to multiply the arguments, x squared times x plus 1. So you could leave this as your final answer, but I think I personally would prefer x cubed plus x squared if you distribute that in. So this would be my single log answer. I condensed it down from 2 logs to 1. If we take a look at the second example, where we have a power out front, we are going to try to make all of this into 1 single log, or 1 single log base 3. So I'm going to move that 1/2 in just a minute. But the first thing I want to do is leave the 1/2, and I'm going to work on stuff in here. Every single exponent first, I'm going to move back up. So we'd have log base 3 of x cubed plus log base 3 of y to the second, and then minus log base 3 of z to the fourth. And now my goal is to figure out how to get all of this to be a single log. Well, let's take a look at something. If we have 2 separate logs being added, that means that we're really multiplying inside a single log. And if I have a log being subtracted like this one, we're really ending up dividing the logs. So here's what we end up doing here. I'm going to leave the 1/2 for now. But these 2 logs, everything is going to be log base 3 because all of these are log base 3. Because these 2 logs are being added, both the x cubed and the y squared are multiplying each other in the numerator. But because this log base 3 of z to the fourth is being subtracted, the z to the fourth is going to divide and be in the denominator. And so again, 2 things being added, head up in the numerator. If you're subtracting 1 thing, that goes into my denominator because I'm dividing it. The last thing we need to do, or I guess second to last step, is that 1/2 is going to come up to the top because it needs to condense more. So we'd have log base 3 of x cubed times y to the second over z to the fourth, all raised to the 1/2 power. But if we're still condensing, the 1/2 really means square root. So we'd have log base 3 of the giant square root of x cubed times y to the second over z to the fourth. This would be my final log completely condensed. And this example reminds me a lot of the one we did on the previous page. It reminds me of what we did here. This is the original problem. This is the condensed version. We expanded it out. This example was already expanded, and we condensed it back to look like the previous one. If we take a look at the third example, first thing I want to do is move those exponents. So this would become ln of x to the 1/5 power. plus ln of y plus 2 to the third power minus ln of z to the seventh power. Now that I have the exponents raised back up, actually this problem ends up being similar to this problem, that I have two different logs here being added, or two different ln's. So that's really ln of x to the 1/5 times y plus 2 to the third, because again, I'm using this rule of two different logs being added is the same as a single log of the arguments being multiplied. Because this ln is being subtracted, the z to the seventh is going to divide to the bottom. So we have it almost condensed. The only last thing I would want you to do is simplify this piece. If x to the 1/2 is a square root, x to the 1/5 is a fifth root. So this means you have a fifth root of x times y plus 2 to the third over z to the seventh. There is no reason to actually multiply out y plus 2 to the third. That's more work than we need to do. So this next example, again, let's worry about our exponents first when we are condensing. We don't have an exponent on this one, so it'd still be log of x plus 1. But then this next one will become log y to the 8th, and then minus log z to the 1/3. Now this problem ends up being a little bit different than this one. Similar logic, but notice that this example we had a plus here, so we put both on top. This example, we have two things being subtracted. So just like, let me go back to a previous example, just like this one, where we ended up noticing that when we subtracted two things, they originally both were in the denominator. So this example, if we want to make this into a single log, we'd have log of, let me try that again. That was just awful. We would have log of x plus 1 in the numerator because it's first. But then we are subtracting both of these. So you're really subtracting a sum, which ends up being subtracting both of them. So y to the 8th and z to the 1/3 end up going on the bottom. To explain that a different way that did help students in past years, if you take a look at this situation, this is really the same as log of x plus 1 minus, if you take a negative out of both of these, you end up getting log y to the 8th plus log z to the 1/3. Because if you take a negative out or distribute out a negative or factor out a negative, you end up getting negative, and then both of these change to a positive. So the reason that the bottom has a multiplication here is because you're using the idea that two logs being added leads to a multiplication. And again, if both of them are subtracted, they both end up on the bottom. So I thought that this might help some of you if you're interested in that. But anyway, if we continue with this problem to completely expand it, the only thing we'd have to do, or completely condense it, what we'd have to do is just change this to a radical. So my final answer would be log of x plus 1 on the top, and the bottom would be y to the 8th times the cube root of z. So this last example I just wanted to put in here to show you kind of a cool relationship. This one, log base 9 of 243. So when you look at it, you definitely could use the change of base formula, and you could just plug it in the calculator and get log of 243 over log of 9, and you would get an answer that way. But just to show you a cool connection, so to the rules for today, if I have log base 9 of 243, 243 can actually be written as an exponent. 3 to the 5th is really 243. So what you could do is change this to log base 9 of 3 to the 5th. And then if you have an exponent on top, you would bring it down in front. So you'd have 5 log base 9 of 3. And you might remember from previous videos that log base 9 of 3 is really an exponent. What exponent is it? Well, 9 to the what equals 3. Well, the relationship is that the square root of 9 is 3, and square root is really to the 1/2 power. So that means that this entire thing is just replaced with the exponent of 1/2, but that is still multiplying by 5, so the answer would be 5/2 or 2.5. If you plug this into your calculator, you would also get 2.5, but I thought some of you might appreciate the relationships between the rules that we just did today and things we did in previous videos. That logs are exponents. This exponent is really to the 1/2 power. Multiply that by 5. Got your answer without a calculator. All right, guys, thank you for listening to this definitely longer video. I wanted to make sure to be thorough, though, for you, and feel free to rewatch and come visit if you have any more questions.